Well, I'm driving back from Charlotte, and I just got done attending a 2-day heat load calculation and right soft class taught by pretty much the best in the business, Alex Meany. And I tell you, it's just really awesome to be able to be taught by people that are industry recognized as being some of the best. And I enjoy surrounding myself with people like that and being the dumbest guy in the room. When you're the smartest person in the room, either in reality or maybe in your own head, you don't grow, you don't learn anything. And we all know people like that have to sound off and sound like they're smarter than everyone else, but if you really know what you're talking about, what they're talking about, you realize how little they know. But the reason why I'm talking about this is because I look back at my formative years as a technician and how heat load calculations were just this voodoo, this mystery that we as lowly technicians just were never going to be able to learn about. And it was just considered this thing that was completely above our heads. And I think there's a lot of that in this industry. Controls was another thing. We had a controls department, and these guys just came in on their high horses, and they just acted like this stuff was unlearnable to the normal person. And the reality is nothing in our industry is out of our reach. And if you're being told that, or that's a culture in your company, then it's not true. Heat load calculations are very learnable. It's a very simple concept, and all you have to do is think about an Igloo cooler versus a Yeti cooler. What makes a Yeti cooler so good? Well, it's well insulated, it's well sealed. What makes any cooler more effective? Well, you have to close the lid. If you leave your cooler open, how good is it going to be at keeping your food cool, at keeping the heat outside instead of inside the cooler? And that teaches us a lot about insulation and air sealing. Of course, there's a lot more to heat load calculations than that, but pretty much it's a process of measuring the three forms that heat makes its way from the hot outside or the cold outside into the indoors where we don't want it. And those three ways that heat is transferred is conduction, convection, and radiation. Conduction is literally how the heat transmits through the walls, and how fast it goes through the walls is its transmission coefficient. The higher that number is, the closer that number is to 1.0, the more conductive that wall is. The inverse of the conductivity or the transmission value of a wall is its R value. So that's just the opposite of the U value. So the higher the R value, the more resistive or the more insulated a wall is. When it comes to convection, we're pretty much talking about leaks and cracks and infiltration, how air and heat and moisture and energy can leak its way in and out. And finally, radiation is the effect that the sun has on the building, especially on glass, because the sun travels through outer space and it doesn't eat anything up until it hits an object like a building or glass, and then those electromagnetic waves, they vibrate when they hit that surface and they create heat. But all a heat load calculation is understanding how to measure those things or how to calculate those things. At the end of the day, it is still a scientific wild guess. The process helps us take a lot of the guesswork out, but it's still a scientific guess. Because think about any kind of wall. You've got a wall, 2x4 studs, 16 on center. You've got insulation in between. So you may be able to understand the R value of that wall as an assembly, but all of a sudden you put a window in that wall, and that window has framing in it, and that framing is what you call a thermal bridge. And the thermal bridge doesn't have a lot of R value to it. It lets the heat transfer right through it. And wood is not really an insulator. It's actually more of a conductor when it's compared to insulation. So you can have a wall that's got R15 insulation on it, and it performs a certain way, or you can have a wall with a window and a bunch of framing to support the window, and more wood and less insulation, and that wall is going to have a different performance factor. So there's a lot of unknowns that are really hard to calculate in the manual J heat load calculation, but you do the best you can to get as close as possible. The problem is when we start making decisions on replacing equipment and making other decisions that are not based on any math at all, but rather based on rules of thumb, that's where we get in trouble, because our industry is changing, and those rules of thumb that used to work years ago don't work anymore because houses are tighter, they're better insulated. We've got more humidity in the air now because of the way our climate is reacting to certain things, and all that changes what those rules of thumb should be. So you as a technician, don't get intimidated by things like HVAC design. Don't think that it's above you, that you'll never learn it, so you might as well just use these rules of thumb because that's all you can handle. Trust me, you can learn HVAC design just like I did, and it's eye-opening. When I finally went for my contractor's license, I had to learn Manual J, Manual S, Manual D. That was my first introduction to those ACA design manuals, and it was in a prep class to help me to pass the test, and it was eye-opening. I realized just how much impact that the building has on the amount of HVAC that needs to go in the building, and how the two are intertwined. And that is what got me interested in building science and home performance, was going for my contractor's license and understanding HVAC design. So don't leave yourself out of it. Don't deprive yourself of that experience and that knowledge, because just like me, once you get over that hump and you start to learn how these things interact with one another, it'll change your life.